Yeah, I apologize for the word salad on this slide. It's actually quite a bit of stuff and quite a bit of work that's been going on, and the major problem is that it ends up being this large body of work to get a few very specific things done, but well, I hope you'll find it's worth it in the long run, right? So first, I will talk about this motivation that's got me doing all of these massive changes that breaks everyone's back ends that are out of tree, for which I apologize in advance, by the way. I'll then talk about some of the current status, where I am in the middle of the changes, some of the changes that I'm going to need to make, including things like IR changes, front-end changes, and that kind of stuff. And then I'm going to talk about future work, including some future very specific directions, some future not so specific directions, and things like that. And we'll see where we get from there, and then hopefully answer a few questions. So motivation. Where are we coming from? So we're coming from an area where we can generate code for a specific machine, Power 7, Power 8, Cortex A57, Nehalem, Haswell, something like that, at a time, right? So, but we have these things like link time optimization and what I'm going to call architecture interworking, which kind of steals from the ARM terminology of the ARM thumb native interworking that they had for a while, where we want to do things that are a little different. And then we have function multiversioning. I will go into exactly what it is, but it's a source level feature that GCC implemented a while back. It's very, very useful performance-wise, and hopefully I'll convince you exactly how useful and how cool it is and what we can do with it. So sub-target architecture support, what do I mean by this? I mean all of that, and that, and that. And I threw in MIPS 3D just because it's kind of fun. And even VSX for Bill. So we want to support all of these things at once. We can't do that right now. And we also want to support more MIPS stuff, because MIPS has this kind of fun stuff where you get to call from MIPS 16 to not MIPS 16 and all that kind of stuff. These are kind of contrived examples, but they're actual working code that involve a lot of hacks in LLVM to get this stuff to work correctly. A ridiculous amount of hacks throughout the entire compiler. And then we want to do sub-target LTO, which is probably something more near and dear to everyone's heart, right? Let's say we compiled something for AVX2, or we compile something not for AVX2, something else for AVX2. We link them together and we code gen. What do we actually get? We don't get AVX2, right? So why is this important? And some code. So what we have here is we have an AVX-specific function that's calling all of the AES, everything. We've got a generic one that implements AES keygen assist in 1,000 lines of code or whatever it ends up being. And then what we end up doing is in the main function, we end up checking for CPU features. We check to see if we have AVX2. We check to see if we manage to link that shared library in, and then we actually make the phone call for our function. We dial out to everything. So this is a lot of code and a lot of work to just do something that's pretty simple. So enter function multiversioning. We avoid splitting code between files, because to do the previous version, you can't compile that in the same file, right? You have to split it out, because again, AVX for one file, not AVX. So it also avoids expensive runtime checks. CPU ID, you can cache. It's still not fast, right? And you're probably going to do it in every shared library at least, probably multiple times per program. And honestly, given the size of programs these days, you're probably going to do it 150 times at least in a very small program. It also gives you some serious performance and code size benefits, right? You can do one instruction to do CRC32. One versus the CRC32, hand-coded. Or even using SSE4, you still don't get a whole lot. But if you can do this, you can see like a 4x improvement on your CRC by doing it in hardware. That's huge. I personally have seen that we use CRC32 a lot. I care. So this is what it actually looks like once you use function multiversioning. This is all in one file. You do get to specify your targets. You get to specify your CPU features. You get to specify all these things. It's very handy. It removes a lot of boilerplate. It adds a little bit of boilerplate. It adds some attributes. And it adds some special things under the covers. So let's talk a little bit more about how this is implemented. Does all of this make sense so far to everyone? Any questions? Excellent. So we'll talk about how it works on Linux because that's what I'm most familiar with. So it works via a mechanism called ifunc. Basically, functions are specially mangled. They end up having a final little string concatenated to them, .sse3, .avx, everything like that. It's very simple. It's not a problem. All calls end up going through the PLT for these kinds of functions. So everything is an indirect call. And this is important because it means that you can use a dispatch function at program load time to resolve relocations into the PLT to make your indirect call just a simple indirect call on x86 or any other architecture that happens to be able to just take a load from the PLT, make a call. It is a special symbol type. It does require a special relocation. It requires, therefore, assembler support, linker support, loader support, and a little bit of compiler support. So it's not a set of function pointers, right? We could do this using a set of function pointers, right? We could initialize. Yeah, it's another function call to do your function table, right? To set up your function table, which means another call through the PLT for your shared library. So we've got three more PLT calls now, calls through the PLT, then the indirect call through the function table. And with ifunc, the PLT instantly resolves. It's just a simple indirect call at every location. Solves a lot of problems. So hopefully with all of that motivation, this is what the final IR is going to end up looking like for our simple test case. Our simple test case here just has a bunch of functions that return some floating point. On x86, you can use 3 different instructions to do these 4 different functions. Whether it's vmove ss, move ss, or using the x87 floating point stack, which could be exceptionally fun for this. So this is kind of the ideal world that I see us moving to, where every function has the target CPU, which could be, in fact, Core i7 as a little slight difference as opposed to the standard triple, which is why it's in there as an illustration. And then you've got your target features for that particular CPU. It works the same way that you would with the matter string that you would pass into LLC or anything like that to do backend work. So it ends up with a very simple interface to extending, and it's the same feature string that you would pass in anyways to the target machine. So speaking of the target machine, where are we? Because the target machine, it turns out, had problems. So there was an attempt to do this work in the past to reset the subtarget on every function boundary to something that would generate code for that particular subtarget. It would parse the target CPU and the target features the way I've got it even off of the function. It would go, all right, what do we get from here? The problem was that only worked for instruction selection. It didn't work for optimization. So target transform info didn't work. The vectorizer didn't work. Based on Chandler's talk earlier today, we also wouldn't get parallel code generation. And I kind of want parallel code generation. Even better, it doesn't work on this. It wouldn't even work on our little simple, this is our ideal world where we wanted to use a particular, one instruction to do a constant load. So it's not really the ideal world. So I started playing around with this and figuring out what it would take. And what it takes is looking at the target machine. So since we can't reset parts of the target machine, we actually have to look into making the target machine work for every function. We can no longer hard code things. We can no longer let things hard code through the back end. We can't cache things anymore as well as we could. But it ends up with a slightly cleaner interface. So the target machine right now, or before I started this, contained target options. All right. The subtarget, okay. The data layout, fairly important. Instruction selection information, all of it, just for the subtarget though. Frame lowering, scheduling, pass manager, that's in the target machine, don't forget. Object file layout, all the object file layout stuff is also in the target machine. So remember, subtarget as part of the target machine, instruction selection, which is part of the subtarget, frame lowering, subtarget, scheduling, subtarget. So let's remove all these things, right, and see where we actually get to. Now we've got target options, data layout coming soon. I moved it because so many targets had the data layout being subtarget dependent. Turns out this is a problem because then your ABI changes between functions. So if you're on ARM and you decide to swap subtargets between functions, you've just changed your ABI. If nothing else, your function alignment just changed between functions. Sometimes, for a couple of targets, your integer size changed, which was particularly unpleasant to notice. So we're going to move that back up to the target machine. Actually, I'm going to go back one second. So that's really important. The data layout ends up being very important for globals. Structure layout is where data layout really is key and has to be on the target machine, because it's the global layout for your global variables, right? You can't just say, well, you know, the variables in this function can be aligned to 32 bytes and the ones in this other function are 16, and integer sizes can be different between these two functions, which would be very exciting, but we can go with it. It's actually your globals. Your globals won't work otherwise. So the pass manager is going to stay on the target machine unless Chandler has other ideas. Yeah, he's looking at me, so. Object file layout should stay on the target machine just for that ABI idea. Basically, the target machine is going to handle the pass manager over here, and then everything that's important for data layout and your general target features. You know, is this an x86? Is this ARM? Not is this ARM or thumb, just is this ARM eventually. Is this MIPS? Is this, you know, NVPTX or, you know, Hexagon, whatever. What is the base target machine? All of that plus all of the ABI stuff to generate an object file is going to be on the target machine, and that's it. That's all that's going to be there. So you notice the subtarget wasn't in this list back here, right? So I added a subtarget cache. Basically, we need some way to look up the subtarget based on our CPU, based on our feature string, based on all of these things. What are we going to do? Well, get subtarget still exists. You can still get the subtarget when you need it, except it's a little different. It takes a function now, because we're going to add all of these features to our functions to describe what features and what CPUs and what features they need, right? And then we're just going to have, right now I have a simple string map. If anyone has a better solution, I'm all ears, but right now we just do some code that looks about like this to create a subtarget. I cheated a little bit. This isn't actually the full x86 one because some targets have specific subtarget features they want, like that are attributes on functions. So any target that has a target feature that is its own particular attribute that it can apply to a function is going to need to do a little bit extra work, but there are examples in the code base already. In particular, x86 has soft float. So you need to come up with some way to handle soft float in here. But this is the entire code to grab a subtarget, to grab a new subtarget per function, and you can cache it, and it just looks it up. So there is a problem with this code, though, that needs to be fixed. It's on the list, you know, help requested. I'm, you know, currently 4 or 5 yaks deep in my shaving. It's reset target options. So this is what's going to impede us from being able to do parallel code generation right now, because we reset some global variables every time we want to compile a function. And unfortunately, we have to reset it every time we want to look at a new subtarget, because some of the subtarget initialization is based on these target features. Those all need to move down to the functions. It's a lot of typing. It's not actually hard. It's just a lot of typing that I haven't gotten quite to yet. So more on the subtarget cache. I implement it for these targets. There are a few that are trivial to implement for other architectures. I haven't done it yet because I figure we have enough target maintainers around that they can probably implement a couple of them. And really, if you don't care about switching subtargets, you don't have to implement it. You can keep the one subtarget you've got and use that. But if you want to use any of these actual features, some of the code's going to be going away, but there are shims that work. So. Then there's the middle end. So I've covered the back end and code generation. Then there's the middle end. So target transform info uses a lot of subtarget specific information. It thrives on subtarget specific information. So unfortunately, the pass manager doesn't support boundary crossing analysis passes. See conversation earlier this morning. So we need a function specific TTI. It's a hack. I admit it's a hack. I don't even think there's a good solution in Chandler's new pass manager to solve this problem. So what do you have to do? You have to do this. It's a shim, right? All it does is, as a function pass, it takes the function, it stores it, and it passes it along to TTI. Why are we writing a shim? Because changing every single location is so much churn. It makes the previous patches I was doing look somewhat nice by comparison. And this way, most of the actual uses in the code don't change much outside of, oh, it was a TTI call, well, now it's a function TTI. It still needs a TTI, it needs the function, you're set. And TTI, as far as I know, isn't used in any module passes, so we're not going to run into problems there. So, future work. Realize this is going a bit fast, but I've gotten a lot of questions on this over the years, so I added a little bit of extra time on the idea that I'd probably be getting a few questions. So the IR changes that are going to be required, and we go back to the function multiversioning, right? So we're going to need the function attribute, CPU, and feature string. I have a patch. It needs some testing. It's trivial. It'll go in, right? That's going to be easy, though. Anyone that looks for all of these kinds of things in the function attributes, it's going to have more data. It's going to be more complete. It'll have more stuff, right? It's fine. It'll look like this. It's not particularly exciting, but it actually conveys and carries a lot of information. What else do we need? We need a new call and invoke destination for ifunc calls. So we need something new that we can call in the IR that is not just the kind of values that we have. We need a new value that we can call, which means that we can create the dispatch, create the relocation, or the associated assembly for it, and make sure that it all gets propagated through to the back end so that we know that we're creating all of this dispatch, that we know that we have the relocations, that we can then funnel all of this information through to the dynamic loader. So I don't think this is going to be controversial, but I've been surprised before. So
I've gotten used to attributes in the function, and then whenever you call a function that has the attributes, you just lower it as a special type of call that has the relocations of the
So he's asking if we can do a special attribute for it. These attributes aren't related to the call invoke destination.
No, on the callee. So if you call that function.
Right, but you don't know because you don't know which one you're calling because you're calling something that is relocated in at runtime, right?
Sure.
Right. Thought about that. That was my first thing. Oh, I'll just put an attribute on the. No, I can't do that. So, yeah, unfortunately, that's not going to work. But on the bright side, that gets us to the fun stuff, right? Optimization directions. What can we actually do with this other than, well, create CRC32s that are 4x faster and actually do proper LTO and everything else I mentioned? because that's not enough, right? Well, we can do CFG cloning and inline those really hot functions by creating function-specific versions as we clone up the CFG. What we'll end up doing is saying, all right, here's my SSE4 specific one, here's my AVX specific one. These are both really hot. I have profile information that says these things are particularly hot and they really want to be inlined, right? Well, I need to inline them, but I don't have a function-specific one. We get to start cloning various subsets of CFG and going up. We'll duplicate code, but the idea is that the result will be much faster for a little bit of code size loss. If you're familiar with the way Darwin does multi-architecture slices as far as their fat binaries, basically what this is going to get us is a single binary with fat CFGs that you call through and get a lot of the benefits of multi-architecture slices on ELF platforms without having to worry about going through and duplicating all of the code just when we have a few hot functions or a few functions that would benefit from specific architectures, right? Auto vectorization, because naming things in computer science is hard. I have a vision for this. What I really ultimately want to do is being able to say, all right, I am compiling a lot of code. I care about these 4 or 5 different processors. Go to work. Tell me, if you can get better vectorizations for AVX and SSE versus SSE4 versus some generic code that isn't going to vectorize, well, give me versions of this function that work for both AVX and SSE4. Please, and then CFG clone it all the way up. Give me my fast code and do it automatically so I don't have to worry about it. So that's kind of, closer to the pie in the sky, but it's not too much of an extension past the existing work that we're doing, right? We already have auto vectorization. We already have soon ways to code gen things. We have target transform info, which says, all right, what's good to vectorize here for the vector sizes I've got. All that takes is a simple loop to say, well, can I do more vectorization if I ratchet the number of vector types I've got up? So it's one of those I think it's a very simple idea that should get us some really fun directions here.
Do you want to call the vectorizer many times, one for each type of instruction set?
Yeah, basically.
Which one is the best?
Yeah.
Great.
Yeah. Even better, keep 2 or 3 of them around if they're all particularly good, right? Watch code bloat. Yeah. Watch the code bloat. Advanced idiom recognition. So we already have an idiom recognizer, but maybe with our sub-target knowledge and our advanced knowledge of what types are valid, we can do some better idiom recognition. Instead of B-swap, we can recognize that someone did, okay, AES might be a bit much, but work with me on this one. This is more of a hand-wavy kind of thing, but I have ideas, and I think we can get some advanced idiom recognition. So, questions about any of the code changes I've made, how to fix your broken backends, how to where is this going, what do I have planned, what do we got? We're going to need a mic.
So just going back to one of your earlier slides when you listed out the attributes that were still part of the target machine.
Yep.
So
I fixed your target, by the way.
Okay, so I guess my question is.
I did.
Okay, well, this is just a question. So I see there's data layout out there and there's pass manager on there. So if there are two sub-targets that say have different data layouts or use different passes, does that mean there should actually be different target machines for those?
Currently, yes.
Okay.
Yeah. If you expect to be able to switch data layouts between 2 different, you can't, yeah. Basically, you're going to need 2 different target machines for it.
Okay.
Yeah.
Thanks.
John? How about John, since he got his hand up actually second? And this is going to be terrible, so I'm just waiting.
What were you actually thinking about in terms of the callee for an ifunct symbol?
Like the IR?
Yeah.
I was thinking of just a new IR value for it.
So a new constant
Yeah.
kind? Okay.
Chandler, I think, has a comment on that.
It sounds a lot like a global variable with an initializer, where the initializer turns into the relocation called
It
function.
does, yeah. But Raphael and I have talked about this, and Raphael is waving his hand in the back. This is fun. I just get to point to all the conversations I've had on this subject.
It looks a bit more than just a local global alias, since it has the same value as the resolver function. So it's probably just a bit on a global alias saying this is an ifunc instead of a regular symbol.
Yep, which is kind of the idea I've got right now. All right, so hopefully the symbol thing is mostly taken care of, but that's the basic idea. It'll be proposed. We'll get 1 second, Nathan and Renato.
So quickly, I have a problem that is related to this, which is in the assembly file that we have these .fpu sections, directives that change from then on. And so if I have these kind of things, and if in the same file I have AVX, SSE, and I do a .fpu AVX, and I run something, and then
As
.fpu
inline
SSE.
assembly?
No, even
Okay.
so when you print the when you print the assembly file,
Sure.
right, you would have .fpu to change, because you can't have the thing at the top.
Right.
Right? So the problem is that currently the GNU assembler, if you say .fpu SSE and you run something, and then after that you don't want SSE anymore, it's still valid. Which
Yep.
means if the compiler generates the wrong instruction set,
Yep.
it will be ignored.
Yep.
Right? So I have that issue now. And
For ARM, I know.
I know. And I don't want you creating more problems in that area without discussing the range in which the attribute is valid.
That's fair.
Okay. Because I'll have to fix this in ARM, and then...
Yep.
Okay, good.
You're going to have to fix this in ARM. Yeah. 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 Basically, you're going to have to fix this, and especially if you're relying on anything textual, you may have to change the assembly syntax.
Yes.
I would suggest push and pop.
Yes.
Okay,
Nathan?
going back, yeah, I might be being dumb, but because I don't know the internals of LLVM enough.
That's okay.
But the thing about ifunc is the callers don't need to know at the source level, at that level, that they're calling an ifunc thing. It's the static linker that does the right magic. So I don't quite understand why you need a new...
It doesn't quite work out like that, because it ends up being, because if you look at the way GCC emits the assembly, because remember, it goes through the assembler, so it actually has to know the call target is a possible ifunc function when it emits assembly. I'm pretty sure, at
I
least.
don't think it does.
No?
The static linker needs to know it, but it may be you need it here because you've got the definition of the actual instances that will be resolved in the same translation unit, and you have to say, yeah, no, don't.
I could be wrong. As I said, I didn't implement the ifunc stuff in binutils, so
yeah,
I'm willing to go with...
My interaction with it is implementing the attribute in GCC.
But if we're going to emit a fully linked binary out of LLVM at all, we're still going to have to know about call targets at some point. So,
okay, thanks.
Needless to say, if you want ifunc for, say, the JIT, you're going to need to be able to do this anyways. So, Chandler?
That was a beautiful segue to the question I wanted to ask. Well, comment I wanted to make. So the thing that you do have to know in the compiler is you have to be able to emit the correct relocation.
Yeah.
That's it. And you just do not emit a bad relocation, which is
right.
easy.
You can't. Yeah, you can't emit the actual. Since everything has to go through the PLT, you can't emit you can't optimize it down to a single local branch. Is what you can't do.
You can't tail call it.
You can't tail call it. You can't. Yeah. There are specific things you can't do with these.
So the other thing I wanted to just mention is the The other reason to model this in the IR is so that you can do inlining through it and the CFG cloning. But you mentioned doing CFG cloning after auto-vectorization, and I actually don't think we'll need to. One of the nice things about the way we currently do vectorization is that it's after all the inlining has happened. And so at the time we go to vectorize a function, we already think we have a roughly cromulent size of function to run fast, right? And so like, you don't need to rerun the inliner in any sense. You just need to clone the entire function that you're vectorizing within.
So I will agree that is one possible solution. However, what if you would like to optimize it for multiple versions at the same time?
No, I'm suggesting that you, in that scenario,
Right.
you've already inlined, like you had one function, right? You've already inlined until it's like a nice big fat healthy meaty function.
Oh, well, okay, sure.
Right?
Yeah, no, I see where you're going. Okay,
Right?
yes.
And so the auto vectorizer just needs to clone that big function in times for the in architectures it wants to have available
Sure.
and make the color be an iFunc color.
Sure.
So I think the only thing you have to do is teach the inliner to clone function bodies when doing an inline of an iFunc call site.
Yes. At the very least, I agree that is the only thing I have to teach the inliner. So yes. Rafael has something in the back. As a note, this is a very worldwide developer conference, and the only people that have asked me questions are people that I know all of their first names. So please, anyone else that has any questions, I would love to hear as well.
So you mentioned the JIT, so I have to ask, like, what do you do for cross-targeting?
Oh, I have no idea.
With an iFunc, do you compile just the iFunc for the host?
I would hope so, yeah. I would hope so, but keep in mind that we do support saving JITted code out, and I don't know, you want to have your debugger debugging things across the wire to 4 different machines at once because you're stepping through your multi-process thing. I don't know, man. But it might be fun. Anyone else? Is it that scary? Okay, Tom? See, again.
So my other question is, so in your examples, you had like 4 functions for 4 subtargets. Is there some way to have just a single IR function and then generate code for multiple subtargets from that?
Yes, I didn't. I've said it, but I didn't actually write it down. Yeah, I didn't actually write it down. I apologize. One of the ideas I have is actually, remember when I said I wanted to pass in a bunch of architecture targets and go, just
Okay.
optimize me, right? So you can pass a bunch of targets and say, hey, find some code that would be good to optimize this way. A lot of this came out of wanting and being able to use intrinsics in a single file and say, call without that obnoxious call overhead of checking CPU ID. The one thing, by the way, that no one has asked me and I appreciate is what do you do to all of those header files that have the ifdefs in them? That starts to get to be the unfortunate thing. So what ends up happening right now is if you don't say I have AVX and you include the I would like some AVX intrinsics header, it goes, but you didn't enable AVX. What it means in this new world, it means you enable it anyways. And you're going to start getting problems at code generation. Now, the idea I have is to have the front end recognize attributes on functions. Now, this won't work with your magical, like, optimize me some functions, but you can assume that every function has this attribute on it and do some checking to make sure that you at least specified the correct attributes for the correct function or the correct attributes for the intrinsics that you'd like to use. So it will require a little more time in the front end to get some better error checking, but it's much better than cannot yet select and something that looks terrible from the back end. All right, Jim.
It's different than version info, but that sounds an awful lot like availability macros. You can use the same kind of thing and say, put
Yeah.
an actual attribute on
It
all of
does.
those intrinsics that will check,
at the point where they're used is a point where the prototype is declared, whether that is available, and get nice, pretty clangified diagnostics on a per function basis.
Perfect.
That also requires going through and putting those attributes on every single intrinsic definition in every single header file.
Do I have
Have
any
fun.
tooling experts in the room? I think I'll be talking to Manuel about this. Anyone else? Anyone with any out-of-tree targets? Paul actually has a question, which I'm surprised. Oh, I know what you're going to ask. Okay. And the answer is I don't know. Let's see if it's correct.
First, let me say it's not my fault that you already know everyone. So, I mean, I like this. It's a beautiful thing. My employer doesn't care because we only have one chip that we care about. And I just want to make sure that no gain, no pain.
Correct.
So as long as we can make sure not to use these new calls and invokes, we're good.
Mm-hmm.
All right.
Yeah, hopefully the front end support as far as, erroring out if you do something stupid, doesn't propagate to the back end before it actually does something. So you at least get some decent diagnostics. It will probably require, as Jim said, availability macros or something similar to make it very nice. But yeah, no gain, no pain.
Awesome.
And I've already, as I said, I've already updated pretty much every port in the tree. So anything in tree should mostly work at this point. If you have out of tree ports, hopefully you've already noticed. If not, I can tell you what to do.
Yeah, well, our target is, as far as the chip is concerned, it's in tree.
Right.
But we only have the one, we only care about this one. Right. All right, thanks.
Mm-hmm.
So what was the question you thought you would be
I actually
asked?
thought he was going to ask about debug info for ifunct functions, at which point I was just going to throw up my hands and go, that's going to be fun.
So I was wondering if you had some thoughts about generalizing this to different dispatch mechanisms. So I have a particular thing in mind, so I'll tell you. So for the target that I care about, it would actually be really nice to be able to dispatch to different versions of a function depending on how many threads are running. Because the instruction scheduling is actually very different to optimally instruction schedule for when you're running 1 thread per core versus 4 threads per core, et cetera. So I was sort of wondering if this mechanism could be generalized to
for that
kind of
for that mechanism, you're going to want to go back to the function pointer probably idea, because right now this is a runtime relocation, so it gets hooked up at program load time. Mm. So you're not going to be able to use this exact mechanism for it, but if you want to generalize it, you'd probably want to generalize it to, well, if I want to do this per number of threads that are running at the time, then you'll probably want to do the function pointer table.
Right. So I mean, I suppose not the actual ifunc stuff, right? But the sort of, the IR level.
The IR level stuff should be possible. We'll probably just want to version it for via either target options or some sort of code generation option to do it. But yeah, I don't see it should be easily generalizable.
Cool.
I don't see anything wrong with it.
Sorry, I might have missed it, but so once you start running your application, it runs on the same sub-target no matter what, right? Don't you just want to pay the price of running on this particular architecture just once? Let's say have some runtime linker support that will do the patching for you before the program starts executing?
Oh, like pre-relocate these relocations after you've run it once on the...
Exactly.
Yeah, that would work. You can probably use some of the existing Linux support for doing that and just patching them in. I don't currently have plans to do that, but it should be fairly simple to change the binary if you already know the target of the relocation. I mean, you basically, as part of your install onto a particular machine, you could actually resolve the relocations yourself with a small tool
Yeah,
say,
so this will be the static linking,
Yeah.
And you can also, I guess,
there's-
do it dynamically.
There's no guarantee. No, you can't do it at static link time. You have to do it at like maybe install or a post process if you want to do it for the particular machine that you're executing on. But you're going to run into probably some possible problems because you can't necessarily, this works really well if you're doing only like CPU features or CPU ID checks or something like that. If you have anything more exotic, like, number of threads running, that's going to be really more problematic. But, at runtime, theoretically, you could check the load on the machine as a call when you want to do all of these relocations. Theoretically, mostly you're going to be checking CPU ID for CPU features. So I'm just saying that way lies dragons, but it might actually just work. So.
Again, I guess if you do it not every time when you start the application, I guess you can also eliminate all the redundant functions.
Yeah, as I said, at
there is
install time,
opportunity, I guess, for link time optimization.
right? But then again, if you're
time.
yeah, this gets you, I guess, the same ability that in I guess the Darwin-y kind of way, you would say, you would just delete all the other slices the minute you got at install for on a machine. It's the same general idea. You wouldn't have a fairly universal binary. You'd have something that's very architecture specific. You might be better off just actually flat compiling for your one particular processor that you're going to compile for. But if you've got 6 or 7 that you actually want to detect the processor features, but that your binary isn't going to be moved off machine, then yeah, this will work. Right. Keep in mind that your binary then couldn't be moved off the machine as far as that. It's basically you're doing the same pre-linking stuff that you would normally do.
Right. Okay.
Okay.
Cool.
Yeah, you can add this to pre-link though on Linux if you wanted to. It is different to pre-link, but you could. Yeah, as it's different, but it'll work. With the hand wavy, a simple matter of programming, right? It's not going to be hard. How's that? Okay. Yeah. Anyone else? Any other questions? Any broken out of reports? How many people did I break? Aw. Okay, I saw one hand over there. I know I broke Owen at least once. And Ian. Yep. Okay. So apologies. And if there are no more questions, thank you all for a very good developer conference.
Thank you, Eric.